Greetings. I'm Joe French, and I'm coming to you from my classroom in Mount Pleasant, Utah, and this is topic 2.7, the derivatives of cosine of x, sine of x, e to the x, and the natural log of x. So we're going to be looking at several functions that have their own unique derivatives, and we're going to explore these derivatives graphically instead of proving them algebraically. First, let's look at the graph of the cosine, or the sine graph. Let's look at sine of x first. So this is our graph of sine of x, and what we want to do is determine what the graph of the derivative would look like. So first of all, let's bring sine of x up as our graph, and then let's start thinking about what would be happening to our derivative, what kind of values our derivative would take on at various locations on the graph of sine of x, which means we'd be looking at the slopes of the tangent line. So first of all, when I look at this graph, I see it goes up and down and up and down and repeats itself. And I know that if I think about a tangent line, well, a tangent line at the top of a hump here or at the bottom is just a horizontal line with a slope of 0. So if I were going to plot the values of the derivative, I would know that at each of these peaks and valleys, the graph or value of my derivative would be 0 because the slope of the tangent line is 0. So I'm going to put at each of these places negative 3 pi over 2 and negative pi over 2, positive pi over 2, and negative or positive 3 pi over 2. I know that my derivative value will be 0. Now, in between, I look at what's going on, and I look at that halfway point, maybe at 0, I can see that my tangent line appears to be going up, and it appears to be going up. It's hard to tell on this graph because the scale of my x's and y's is different, but it appears that it's definitely positive, and we'll say that it has a slope of 1, which is what it does have. When it's going down again at that halfway point, our slope is going to be negative 1. And over here it's going down, so we'll be at negative 1 again. So at this point, pi. And then as it's going up over here at negative 2 pi, we'll put it at positive 1 again. If I connect these dots, I get an interesting graph. If I turn off my function and look at the blue graph, maybe, well, it's not a very good blue graph, but maybe it suggests some other graph to you. Let's take a look at the actual function here. I'm going to pull out the graph of the derivative. I'll bring back the sine graph and trace through what's going on here. Now, if you look at what we discussed, at each of the values where the graph of sine either peaked or bottomed out, we had a slope of 0, and that's where this green graph is going through the x-axis. It has a y value of 0. Hopefully this graph looks familiar. In fact, let me remove the annotations I've made here. And you can see that our derivative graph is exactly what I hope you expected it to be. The derivative of sine is cosine. Let's go back to looking at the cosine and trying to figure out what its derivative is. It'd be awfully nice if it were the sine graph, wouldn't it? First, let me get rid of some of this writing. And now let's go and look at our cosine graph. First, we're going to remove the function, the sine graph. We'll bring back the cosine graph. And if we think about those same ideas where our graph peaks and valleys will have a slope of 0, so our derivative graph will have a value of 0, where would we have those values of 0? Well, at 0, and then at multiples of pi, we see that we are either at a maximum or a minimum on the cosine graph. So if I start pulling out the graphs of the derivatives as we trace, see how right here at the bottom of the cosine graph, my derivative graph is going through the x-axis and has a value of 0. As we get back up to the top, my graph rises and falls, and it has a value of 0. And as I continue, I get this purple graph. If I look just at the purple graph, is this the graph of the sine graph? What do you think? Well, hopefully you said no, because the graph of the sine graph, if I turn that on, you'll see this red graph rises through the origin as opposed to falling through the origin in our derivative of the cosine graph. So what equation would give us this curve? If it falls instead of rises through the origin, we've reflected the sine graph across the x-axis, which means that this derivative graph is the graph of negative sine of x. So the derivative of the sine of x is the cosine of x, and the derivative of the cosine of x is the negative sine of x. Let's look at the graph of e to the x, exponential graph, which starts out very flat and then rises and starts rising faster and faster and faster. If we think about what that means for a derivative, talk your way through it. What would be the slope of the tangent line over at negative 10 or negative 8 for our x value? Well, the tangent line would be pretty flat, so it would be a pretty flat tangent line, wouldn't it? A value close to 0. And then what happens as we move further out along the x-axis? Well, our tangent line starts getting a larger slope, and a larger slope, and a larger slope. Wait, I'm not tracing the graph of e to the x. I'm supposed to be tracing the derivative of the graph of e to the x. But they're actually the exact same thing. If I turn on my derivative graph, you would see that this graph that I'm creating matches exactly the graph of e to the x. This is a really cool result. As my e to the x gets steeper, so does the values of my slope of my tangent line. In fact, they match exactly. The derivative of e to the x is e to the x. This is the only function where that's true. The derivative and the graph itself are the exact same. No way. Our two graphs are identical. The graph of e to the x and the graph of its derivative. All right, let's look at one more. The graph of the natural log of x, or actually the absolute value of the natural log of x. The natural log of x would be just the right-hand side of this original graph. So getting very close to the y-axis and moving outward, going through 0, 1, and then passing through E1. So 1, 0, and then this point e comma 1 for the graph of the natural log of x. So if we look at what's happening to this graph, what kind of slopes we're talking about, you can see that right next to the y-axis, this graph is going up like crazy. So it's got a huge positive slope. And as we move out, further out, our tangent line is still positive, but it's definitely not as positive. In fact, it looks like it's leveling off. It never quite levels off the natural log of x, but it does grow slower and slower and slower. On the left-hand side, which we can graph because we're taking the absolute value of x, we can't take the natural log of negative numbers, but we can take the natural log of the absolute value of a negative number. And you can see how the graph is reflected over the y-axis. So in this case, as we get closer to 0, the graph gets more and more negative. And as we are looking out here further out to the left, if we draw a tangent line, it's got a negative slope, but it's not nearly as negative as it was close to 0. And again, it starts flattening out the further we go, but it's always just slightly negative. Here, we start way up with a positive slope and end up with a slope that's just barely positive. If we look at that graph, we're going to turn off our e to the x graphs. And if we look at the graph of the natural log of x and look at what happens to that graph, look at the natural log graph, not just the natural log. And if we look at what's happening here, we've got negative slopes, so my derivative graph is just slightly negative. The graph is just slightly going down. As it goes down at a more and more rapid pace, my derivative gets a larger and larger negative value until it drops off and goes. And then once we cross over the x-axis, we start going up, up, up again. So there's this discontinuity at 0. Our derivative graph jumps over the y-axis and becomes a very positive number, which gradually becomes less positive but stays positive as we move further and further out the x-axis. If we look at just the graph of the derivative, not the original, we see this hyperbola type of graph, which hopefully also looks familiar to you. This is the graph of 1 over x. Our derivative graph for the natural log of x is 1 over x, or x to the negative 1. So these are our 4 new derivatives that we can use as we solve problems going forward. The derivative of the sine graph, cosine of x. The derivative of the cosine graph is negative sine of x. The derivative of e to the x, one of my personal favorites, is e to the x. And finally, the graph of the derivative of the natural log of x, or the absolute value of x, is 1 over x. In the next video, we'll go over some examples of how we might use these in some problems.